Alrighty. Yeah, he said I gotta go pretty speedy, so you can find me later if you want to ask any questions. But I'm gonna talk about how Avalanche approached fee mechanism because we revised it a few times, learned some lessons along the way, and hopefully you can learn something from our mistakes. First, I want to clarify that we don't price transactions in general by the number of transactions, right? Like one transaction is not equivalent to another, and we use gas as a proxy for computation quantity. In general, we think it should probably depend on a few other things besides the size, but I'll get to that. And then transaction price normally is broken down into two parts, the base fee and the priority fee. And for all intents and purposes for now, I'm just going to talk about the base fee. So let's make a fake chain. We have gas as our unit of computation, we have some native token, and each validator can process some amount of gas each second. Our first option is, of course, to decide that the gas has some constant price, one token per unit of gas. That's simple. And that's kind of where the pros stop, right? It's difficult to change the price. Lots of times it requires a hard fork in the network, which is complicated. And then the static price means almost always it's incorrect. There's denial of service risks. No one will want to use it if it's too high, ... This is still good for proof of concept chains, permission chains. Solana, for some reason, has a static base fee, but a more sophisticated way of making a market is a first price auction, right? So you bid for a gas price that you're willing to pay, and if you're willing to pay enough, you'll be included. This is good because it does adapt to demand, but it's highly unpredictable. The change in the base fee is unbounded from block to block, and it can be inefficient. Think like crypto summer 2021, Ethereum base fee was crazy, right? This is still common in the Bitcoin fee markets, and priority fees on most chains are an auction. The last option is some black box algorithm. All validators agree on some algorithm to determine the price based off of some other set of characteristics. And that's a little bit simpler, but it's for the user at least. But there's inefficiencies that can happen. This is common in Ethereum. Avalanche does this, why I'm talking about it. And most L2 rollups also do this. So who cares, really? Validators want high priority fees because normally the priority fee goes straight to them. Not on Avalanche, but on Ethereum, Solana, for example, they get that. So that's a low base fee. Active users issuing transactions want low fees because they just don't have to spend as much money. And passive users want a high base fee to burn more coins. So Avalanche had, a few years ago, a static base fee, and that was growing to be insufficient. So we wanted a new mechanism, and we decided on a couple goals. It needed to adapt on the market, it needed low fees for users, and we wanted high throughput on chain. So our first thought, a couple quick notes. The Avalanche's C chain, which I'm talking about right now, is basically the EVM, except for two things. The block times are dynamic. It can be anywhere between 0 and 10 seconds. It's kind of up to the block builder. And no empty blocks are allowed. So if there's no transactions that would be issued, there won't be a block. So our first thought was, why not copy Ethereum? So EIP 1559 up on the board, there's some bound proportional to the distance from the target that the previous block had. And that's the percent change from the previous price. If we were to copy this directly, one very obvious thing would be that we don't have a constant block rate. So lots of small blocks, despite consuming the same amount of gas over time, would cause a bigger change in the base fee. And one small thing that's well known on Ethereum is that we don't really converge to the target over time. Like a 10% increase and a 10% decrease is not the same as zero change, right? So this is a small underutilization if we're aiming to actually consume the entire target. Ignoring that second point, we modified it slightly at first and went with this. So rather than using just the previous block, we had some averaging mechanism over the previous 10 seconds to determine the change. Did that work? I guess. There were some flaws, though. We still had the gas convergence issue, but specifically, there was a minimum base fee of 1 nano of aux, which lots of times is too high. The window specifically had no gas limit, even though the block was bounded. So we could get into this fun situation which you can see here. Blue is the base fee, right? The base fee is growing because the demand is growing, and then the demand goes down. However, the window still has a large amount of gas consumed in it, so the base fee continues to rise. And then no one is willing to pay this base fee. So the network kind of sputters for a little bit. We can't issue an empty block to lower the base fee, and we have to wait for someone to issue a transaction to lower the base fee. That's not great. So we shipped a newer version in like April, I want to say. And we have a rolling target excess. This is highly inspired by EIP 4844. This adapts to the price based on the distance from the target still, but it's symmetric due to this exponential function. I swear I'll show more equations if I have time. There's also a gas capacity with a token bucket. So we do have a bounded amount of gas consumption per unit of time, and that fixes the other issue, right? So now we have symmetric target convergent, we have bounded gas with respect to time, and the block production rate doesn't change the base fee, which is fixing quite a few of the problems that the previous mechanism had. Our first thought was, what if we blindly plug this into our previous historic data and see what happens? And the base fee is lower. I guess that's good. But that's kind of like a circular idea, right? If the base fee was lower, the demand would have been higher. We would have issued more transactions, so the base fee actually would have been higher than shown in this graph. So we tried a simulation. We made a fake demand curve, momentary spikes, and there were transactions randomly sampled from a normal distribution that we added to the mempool. And this is all simulated locally. Using our base fee calculations, we can see that we actually did converge to the target, which was great. Orange is the new mechanism, by the way. And in general, the base fees were lower too, which is surprising since we consumed less gas, but it was our goal, right? We also tuned some of these parameters because we wanted to be able to converge symmetrically, right? And you can see that based off of some of the parameters available in our design, we could have made it double in 60 seconds, but half in 30 seconds or something. We went with symmetry for convenience. Did we fix our issue? Kind of. You can see that weird little blip in February. That was the period of high demand where the minimum base fee was not as much of an issue. And it was approximately close to the target, but we are nailing the target now, right? So that's a big improvement as far as throughput goes on our chain. It wasn't a perfect fix. We're still addressing some of the unintended side effects, I would say, of our new fee mechanism. During high demand, the token bucket doesn't refill very much, so only small transactions will be included, even if a user is willing to pay more. I think I'm out of time, but I hope you guys enjoyed. I would recommend that everyone looks at the actual ACP if you wanted to know more, since there are some pretty interesting equations, but I don't have time to talk about it. I'll be available later for questions.